the Mandelbrot set. Most people have seen this iconic shape, or they have marveled at its beauty and complexity even without knowing they were looking at the Mandelbrot set. This has become kind of the poster child for chaos theory, or maybe even math in general, because it creates such beautiful images. It is also the go-to example for what you can do with complex numbers, and it's literally infinitely deep, infinitely complex, and in my mind, infinitely beautiful. But how does it work? Let's find out. All right, Wikipedia to the rescue. So there we go, Mandelbrot set, enter. All right, the Mandelbrot set is the set of complex numbers C for which the function fz equals z squared plus c does not diverge when... Okay, well, there's a beautiful image, so there's that. And maybe we should try something else first. So let's do something else. Let's go over here, and let's imagine for a moment that we're at a dance competition, right? So here we have the dance floor, and there we have our judges that are going to judge the different couples that are going to dance. And I have the option here to put couples in different spots on the dance floor. So I can, for instance, put a couple over here, and I can put a couple over here, and I can let these couples dance and see how they do. And these couples are going to get judged on how many steps they do before they screw up and go outside of the dance floor. And when they do that, the part of the dance floor where they started gets graded or gets colored based on the number of steps that they took. So these guys, they never went outside of the dance floor. They went to the maximum number of steps allowed in this dance competition. Otherwise, it would take an eternity, literally. So they went to 20 steps, so therefore they get a gold medal, and we make the part of the dance floor over there gold. So let's put some more couples here, and let's see what this entire dance floor looks like. And as I'm putting these couples, I must say that the dance steps that these couples are doing are mathematical dance steps, and they're all the same, and the only thing that is different is that these couples start in a different position. They start their dancing in a different position. So all right, here we go. Let's see how these guys do. So most couples screw up right away, but there are a few that go a little bit longer. So up here were two that went a little bit longer. Over here there was one that went a little bit longer, and over here there is one that will probably go the entire 20 steps. So there we go. So that's also going to be gold. And you'll see that a certain pattern is starting to emerge here. And I said before that the only thing different between these couples is where they start their dance, right? So and right now the dance will start in the middle where the yellow circle is, but I can make this area smaller. So if I make this area smaller, so now I can put 4 couples where before there was only 1. So let's put 4 couples. So 1, 2, 3, 4. And actually let's just put 8 and see what that does. And actually, while we're at it, let's just put a few more over here as well. All right, so now we have, oh, I missed one. Let me go over here. So now we have a total of 12 couples. So let's see what they do. And they start dancing, and a lot of them kind of screw up quite quickly. But we'll see that this pattern is starting to refine itself. And these guys will probably go all the way. And now I can put smaller and smaller, or I can put dancers on smaller and smaller areas. But if I put them one by one, we're going to be here all night. So I made something where I can put a little army of dancers down. So now instead of putting only one dancer, I can put 64 dancers at once. Okay, so 64, 128. So now we have 256 dancers over here. So let's see what they do. And I hope my computer can handle it. So we'll see. Okay, so there's a lot of dancing going on, a lot of quick screw-ups, but there's quite a few that keep dancing for a while. And you'll see a pattern emerge. And maybe you've seen that pattern before. So let's put some more here. And really get the party started. Alright, and over here, and over here, and over there, and over there, and over there, and over there. My computer's gonna explode, but at least we're gonna get somewhere with this. And over here as well. Alright, so this is the end of my computer. Oh, well, so far so good. Yeah, now it's starting to chop like crazy. You can do it! You can do it. Crush through it. Alright, so we're still going. A lot of them are still going. A lot of them are also, they seem to be stationary. And there we go. And now let's get the score for all of these guys. You can do it. Alright, you can see that a certain pattern is starting to emerge here. That is obviously the Mandelbrot Fractal. So that's kind of how that works. And the cool thing is that, well, I should have maybe wait until these guys are finished. But I can zoom in and I can put smaller dancers, or I can put dancers on a smaller area. So if I go over here and let's say I take a point over here and I put 64 dancers on that tiny little spot over there, you will see that they start out dancing very like synchronized as one unit almost, but very quickly after very few steps their behavior will become very erratic and all of them will go in different directions. And this is kind of the idea behind chaos. Is that really small differences in input will result in really large differences in output. And so that just made this little tentacle over here. And if I would keep going, then in the end we would get something like this. Isn't that beautiful? All right, so this making of this image has a few different ingredients. Right, so like the first ingredient would be, for instance, which part of the dance floor we're visualizing. Right now we're visualizing an area that goes from -2, -2 to 2, 2. That's a nice sentence. But we could also obviously visualize a smaller part and just, let's say, get one of these spirals or what have you, right? And we can rotate and do all kinds of stuff. So that's one ingredient, which part of the dance floor we're visualizing. Then there's obviously the judging rules, right? So right now the judging rules were, well, however many steps it takes before a couple screws up and gets out of the dance floor. But there could be different rules. We can look at that later. Then obviously there's how the results are visualized, right? So how do we turn a score into a color? So normally, or what happens very often is that when it's inside of the Mandelbrot set, they color it black. In this case, I colored it a nice shiny gold. And you can color it any color of the rainbow. So we can also look at that. And then last, but certainly not least, is that dance step, right? So what rules do these couples follow when they start dancing? So let's look at that. So if we just go back to Wikipedia for 1 second and we read this again, maybe now this makes a bit more sense. So complex members, let's forget about that. But let's say here, like, so basically it runs this function here, which is the function to get to the next dance step, and the Mandelbrot set is the set of starting points for which the output remains bounded, meaning for which the output doesn't, like for which the dancer does never get outside of a certain limit. So I hope that makes a bit more sense now. So let's take this, this formula here and let's expand on that a little bit. So we have the Fz equals Z squared plus C, right? And let's just point some arrows here and say what we're looking at here. So this Fz is the new position, so it's the position of the new of the next step in the dance. Then over here we have the current position. All right, and last but not least, over here we have the start position. All right, and Z and C are complex numbers. Now, what does that mean, complex numbers? Well, it might mean many different things. I'm not a mathematician, so like there might be other nuances that I'm not getting here. But what I do get from it is that a complex number has two parts to it. It's basically like a vector 2. It has an x and a y component, or like they like to say, a real component, and it has an imaginary component. And I said it's like a vector 2, so the real component is the x component of the vector 2, and the imaginary component is the y component of the vector 2. And this x and y is also the x and y of the image, of the fractal image that we're going to make. So let's just first look at the real component, the x component. So let's just look at the number line. So this would be the x-axis, and it has 0 in the middle, and then we go 1, 2, 3, 4, like whatever. So 1, 2, 3, 4. So this is the positive x direction, and we also have the negative x direction, right? -1, -2, -3, and so on and so forth. This is negative. And this axis, we'll call this axis the real axis. All right. We also have, in complex numbers, an imaginary component, which is on the imaginary axis. All right, so this is the imaginary axis, imaginary, and this also has like numbers going positive over here, and what we like to do over here is say 1i, 2i, 3i, and so on and so forth. Basically, that just says it's 1 in the I direction and it's 2 in the I direction. Similarly, over here we could say it's 1 in the R direction for real, right? Or it's 2 in the R direction, or it's 3 times the R direction. The difference between imaginary numbers and real numbers is that mathematicians have come up with slightly different rules for imaginary numbers than they have for the normal real numbers that we're used to. So for the normal real numbers, you can add them, you can subtract them, you can multiply them, and one of the rules is that 1 times 1 equals 1. Or we could say, like in this case, r times r equals r, right? 1 times 1 is 1. The difference between real and imaginary numbers is that for imaginary numbers, that rule is slightly different. So for imaginary numbers, we don't have I times I equals I. We have I times I equals minus R, or minus 1. All right. So let's see. That's, as far as I know, that's the only difference between imaginary and real numbers. So let's see how that plays out, because over here we're taking we're squaring the number, right? So let's see what happens if we square a number on the real axis. All right. So wait, I can just get rid of the R over here. That was just to make things more clear. So what happens if we square 1? Well, 1 squared is 1 times 1, so that maps to itself, right? If we square 2, that maps to 4, right? Because 2 times 2 equals 4. If we would take 3, it would map to 9, which is like off to the side over there. Okay, great. What happens if we square a negative number? Well, minus 1, if we do minus 1 times minus 1, that also maps to 1. And minus 2 also maps to 4. All right, so it turns out that any negative number, if you square it, it kind of folds over the negative part of the number line onto the positive. So that's a property of real numbers. Now let's see what happens if we square an imaginary number. So over here we square 1i, right? Or oftentimes if it's 1i, to just say we just say I by itself. Well, what happens if we square I? Well, over here it says I times I equals minus r, or minus 1, right? So I squared maps to minus 1. Okay. What happens if we square 2i? Well, 2i is 2 times 2 equals 4 times I, which is minus 1. So we get minus 1 times 4 is minus 4 over here, right? So 2i maps to minus 4 on the real line. All right, what happens if we have a number that has a real component and an imaginary component, which is a complex number? So let's say this number over here, which would be 1r plus 1i, right? Generally, they don't say r. That's my invention. So, and also if it's 1i, then you could just do I by itself. So it's 1 plus I. What happens if we square that? Well, let's see. So we have 1 plus I times 1 plus I. All right. Now we're going to multiply these guys. So 1 times 1 equals 1. Then we're going to multiply these guys. 1 times I equals I. Then we're going to multiply these guys. That's again 1 times I, which is I. And then we're going to multiply I times I. And for I times I, we have a special rule, which is that it's minus 1, right? So I do minus 1. And now I have to group them together. So we have the real parts and the imaginary parts together. So this 1 cancels out with this 1. So 1 minus 1 equals 0. And then we have plus 2 times I. Okay? So it turns out at this point, 1 plus I maps to 2i. Okay, so it looks like multiplying a number by itself on the imaginary axis gives us some sort of rotation, right? It rotates and it scales as well, because from over here to over here, it seems to rotate 90 degrees, but it also scales. So that takes care of this part. Oh, I did it. Screwed up. That takes part of the squaring, but we're not just squaring, we're also adding this c value each time. So what happens to our dancers is that we start at z equals 0, and then we add our c. So let's say this is our starting position. So our c is like this vector over here, and then at the first step we square this number. So if we square this, well, we already figured out, like we get over here, and then we add the c again. And then we square that again, and we go let's say over here, and then we add the c again, and then we like multiply it again, and then we keep going like that each time we add the original offset. And so we get this chaotic dance that either eventually it goes off to infinity over there, or it will stay bounded. So, or it will like just go inside of here forever. But in case of our dancing competition, it will go until the maximum number of steps. So that's kind of how this algorithm works. And so now the last thing to do is to figure out how can we do this complex number thing inside of the computer, which doesn't natively support complex math. So for that, we really only have to look at the at the z squared over there. So the z has an x component, right? And it has an imaginary y component, right? So, and if I square that, I get x plus y I. So again, I'm just going to go over here, I do x times x, so they give me x squared, and then this, and then I'm going to do this one, x, y, so plus x, y, I. Over here, I'm going to get the same thing, plus, that was my girlfriend, x, y, I. And we have the last one over there, which is yi times yi, which is y squared times minus 1. So it's minus y squared, right? And now we have to, let me just make some space over here. And now we just have to group these together by real and imaginary parts. So the real part would be x squared minus y squared. And the imaginary part would be 2xy, if you want. All right. So that is what we can use inside of a computer program to do this dance step each time. So let's have a look at the computer program. All right, so here we have a Mandelbrot Fractal inside of Shader Toy. And let's go through this code over here. So to start with, I have a bunch of code to be able to zoom this, which is not really important right now. It's just so that we can see what we're doing. But like the meat of this algorithm is just over here. So over here we have a loop that goes a number of times. It goes max iter times. In this case, it's 100. This is the maximum number of dance steps we're going to have. So before we had 20, because otherwise the dance would take too long. But now we can do this higher. And the more you want to zoom in, well, here we can't see it, but if we zoomed in enough, then we would need more steps to determine whether we fly off to infinity or we stay bounded, as they say. So like one thing to play with would be just the maximum number of steps. So if I set the maximum number of steps to 10 instead of 100, then you can see that the image becomes less rough at the edges, becomes less refined. So let's see what the difference is between 10 and 20. You can see it gets more refined. It gets closer to the actual edge of the set. And in order to really get to the edge of the set, you would have to do an infinite number of iterations here, which obviously in a computer we can't do. So now we're inside of this loop over here, and here we have this this line of code is just what I explained before. So we start out with something like z equals z squared plus c, and then we do everything that I explained before, and then we get to this, this is x squared minus y squared, right? The x component and the y component, and this is the new real component of my complex number, and then over here we have 2 times x times y. Okay, and then in the end we add the start position, and adding we don't have to do anything special with that, because for imaginary numbers the adding works the same as for real numbers. And then once we've done that, we check, and in this case it's a little bit different from what I showed before at the dance floor example. Here we just check what is the distance or the length. What is the length of the vector z of the current position, which is basically the distance to the origin. And so this says, okay, if you get farther away from the origin, and the origin, I'm not sure exactly where it is on the Mandelbrot, maybe over here. If you get farther away from the origin than 2, then we consider that you have escaped. So in the case of the dance floor, like we had a square dance floor. So you can play with this as well. So you can change the shape of the dance floor. So in this case, the shape of the dance floor would basically be a big circle. You can change this as well and see what it does, right? So I made it smaller now, and now you have, you have a different looking image. So you can play with the shape, and then each time, like it's still on the dance floor, right? Each time it didn't get here, it will increase the score basically. And then once it gets out of this loop, either by going to the max iteration or by failing this test and breaking out of the loop, it gets over here, and here it says, okay, give me this value f, that is my number of steps divided by the total number of steps possible, and that is my final color. So that's basically how the Mandelbrot algorithm works. But you can screw around with things, right? So you could screw around with the dance step over here. So over here I could say, I don't know, let's just see what happens if I, instead of 2 times, I do 3 times. Let's see what happens then. Okay, so where you see that makes a different Mandelbrot set, for which I can't zoom in to a nice spot right now. But you can play around with that, and so okay, so 1.5 maybe. What does that give me? Okay, that gives me a different shape again. And in the case of shaders, because it can do everything in real time, you could even play around with this. So you could even say, okay, let me make a value, or here, let me make a value m, let's say, and my value m is going to change. So I'm going to say float m equals like mix of, let's say, okay, the original value was 2 and the new value was well, actually no, here, let's keep it simple. Let's just do 2 plus the sine of I time. Let's see what that does. Okay, I already used m, so let's use a different one. Let's say h, and then over there h. All right, so I can morph things now. So you can see this is a fun thing to play with. So that's changing the dance step. So let me just put this back to where it was. Another thing we could do is change the visualization of the color. So right now it's pretty much white in the middle and black pretty quickly when you get outside, but it's not completely black. You can see that there is a gradient, right? Well, we can play around with that gradient. So I can say over here, for instance, f equals, let's say, the square root of f, to kind of stretch that gradient out a little bit farther, so you can see more, right? I can even stretch it out farther by like doing something like this. All right, another thing that I could do is I could use this f, because this f value goes between 0 and 1. I could use this f to look up a color from a texture. So let's try that real quick. I don't really have that many exciting textures over here, but if you can make your own texture, then you could make a bunch of textures and you go to Photoshop and you add a bunch of gradients, and now you can select many different gradients that you can use. But for now, let's just say, okay, I take this one over here, this texture, and now I can say, so let's say over here I do, no, hang on, over here I do texture. I hope I do that correct, because I never use textures. I channel 0, and then I have to make some UV coordinate. So let's use f for the UV coordinate, and then .rgb. So let's see. Okay, so you see that creates some sort of weirdly colored situation, and you can play around with this and get lots and lots and lots of different types of effects. Let me put it back to where it was. So I'm just going to go vec3f. Let me see here, one last thing perhaps. We could, for instance, like instead of just checking whether we're outside of the dance floor, like we could have one judge check what was the closest that we got to the x-axis or to the y-axis. So for that you could do something like you make a value over here, you set it to something large, and then over here you say, okay, MA equals the min of MA and the absolute value of, let's say, the X component. So this keeps track of which dance step came the closest to a certain location, or in this case to the horizontal axis in the middle here. And then when we get out of here, we could use that to do something. So let's see here, F equals MA, and this is off the top of my head, so it will probably explode. Okay, well, there you go. So here we have different kinds of patterns now, and we can combine those, and we can come up with any kind of rule basically to come up with different images. And you can really get lost in this and play with this for a long time. There was one that yesterday I was playing around with where I did this, I think, C times C. Okay, so now I have some sort of leaves coming off here, you see. So yeah, so that's basically how the Mandelbrot Fractal works. If this got you excited, please check out my video on how to make a Mandelbrot Explorer. Check it out over here. Or otherwise, I would love to hear from you. Get me some feedback or what you want to hear next. In either case, I will see you next time.